Right now, at this very moment, there's an image sitting on the servers at NASA Goddard Space Flight Center that should not exist. It was captured 3 months ago by the James Webb Space Telescope, pointed at a region of space so distant that the light reaching us left its source more than 13 billion years ago. What that image shows breaks one of the most fundamental assumptions about how the universe works. It shows a galaxy that, according to every model we have built, should not have had enough time to form. It shows structure and organization that requires hundreds of millions of years to develop, appearing in a universe that was barely 300 million years old. The astronomers who first saw this image did not celebrate. They did not immediately publish. They spent weeks double-checking the data because what they were looking at contradicted something so basic, so foundational to cosmology, that if the observation holds up, it means we have been wrong about the early universe in ways we are only beginning to understand. This is not clickbait. This is not exaggeration. This is peer-reviewed data published in November 2025 in the Astrophysical Journal, and it has the entire field of cosmology in what one researcher called organized chaos. If you want space science that respects your intelligence, subscribe to Space Horizon right now because we are going deep and we are not cutting corners. Let us begin. To understand why this discovery is so significant, you need to understand what the James Webb Space Telescope actually is and what it was built to see. Webb launched on December 25th, 2021, and reached its orbital position roughly 1 million miles from Earth in January 2022. It is not in orbit around Earth. It sits at a gravitational balance point called Lagrange point 2, where the combined gravity of the Earth and Sun keeps it in a stable position relative to both. The telescope itself is fundamentally different from Hubble. Where Hubble observes mostly visible light, the kind of light your eyes can see, Webb observes primarily in the infrared. That is not a limitation. That is the entire point. Because light takes time to travel across space when we look at distant galaxies, we are not seeing them as they are now. We are seeing them as they were when the light left them billions of years ago. The farther away something is, the older the light, and the farther back in time we are looking. But there is a problem. As the universe expands, the space between us and those distant galaxies stretches. And as space stretches, it stretches the light traveling through it. Visible light from extremely distant galaxies gets stretched so much that by the time it reaches us, it has shifted all the way into the infrared spectrum. This is called redshift. If you want to see the earliest galaxies, the ones that formed in the first few 100 million years after the Big Bang, you cannot do it with visible light. You need an infrared telescope. You need James Webb. Webb's primary mirror is 6.5 meters across, more than 2.5 times the diameter of Hubble's mirror. It is made of 18 hexagonal segments coated in gold because gold reflects infrared light extremely well. The entire telescope operates at temperatures close to minus 230 degrees Celsius, kept cold by a 5-layer sunshield the size of a tennis court. Every part of this machine was designed with one goal: to see farther back in time than any telescope ever built. And it is working. In its first year of operation, Webb has already imaged galaxies forming less than 400 million years after the Big Bang. For context, the universe is currently 13.8 billion years old. Webb is showing us galaxies that existed when the universe was less than 3% of its current age. That alone would be extraordinary. But what Webb found inside those images is what has scientists genuinely struggling to explain. In July 2022, Webb captured an image of a region of space called SMACS 823. It is a galaxy cluster roughly 4.6 billion light-years away. The cluster itself is not what matters. What matters is that the cluster's enormous gravity bends and magnifies the light from galaxies far behind it, acting like a natural lens. This technique, called gravitational lensing, lets astronomers see galaxies so distant and so faint that they would otherwise be completely invisible. When researchers analyzed the Webb image of SMACS 823, they identified galaxies whose light had been traveling for more than 13 billion years. Galaxies that formed when the universe was only 600 to 800 million years old. That was expected. Webb was built to find exactly those kinds of objects. What was not expected was how those galaxies looked. According to the standard cosmological models, the very first galaxies should be small, irregular, and chaotic. They should look like messy clumps of stars barely held together by gravity, still in the process of assembling into something organized. The reason is simple. Structure takes time. When the universe was only a few 100 million years old, there simply had not been enough time for gravity to pull together the massive, organized, spiral, and elliptical galaxies we see in the nearby universe today. But that is not what Webb saw. The galaxies in the SMACS image and in dozens of follow-up observations taken throughout 2023 and 2024 show clear structure. They show disks, they show spiral arms, they show central bulges. These are not chaotic clumps. These are galaxies that look mature. Galaxies that look like they have already gone through hundreds of millions of years of evolution, appearing in a universe that was barely 300 million years old. In August 2023, a team led by Dr. Ivo Laba at Swinburne University published an analysis of 6 galaxies observed by Webb in a field called the extended Groth strip. The galaxies had redshifts indicating they existed between 500 and 700 million years after the Big Bang. When the team measured the total mass of stars in those galaxies, the numbers did not make sense. One of the galaxies appeared to contain as much stellar mass as the Milky Way. Our galaxy took more than 13 billion years to build that much mass. This galaxy supposedly did it in less than 700 million. Dr. Labe told reporters at the time that if the measurements held up, we were looking at something deeply wrong with our understanding of galaxy formation. Other researchers were more cautious, pointing out that measuring distances and masses at these extreme ranges is difficult and prone to error. But as more data came in, the problem did not go away. It got worse. In February 2024, another team using Webb data identified a galaxy designated JWST 0. Spectroscopic analysis confirmed it existed just 290 million years after the Big Bang. It is currently the most distant galaxy ever confirmed. But distance was not the shocking part. The shocking part was its brightness. The galaxy was far more luminous than models predicted should be possible at that point in cosmic history. Luminosity in a galaxy comes from stars. More stars equals more light. To produce the brightness, Webb observed JADE's GS-Zeph14-0 would need to have formed stars at a rate far exceeding what theoretical models say should have been happening that early. Either star formation in the early universe was vastly more efficient than we thought, or something about our models of how stars form in low metallicity environments is fundamentally incorrect. Then in November 2025, the paper that triggered the current wave of serious concern was published. A team, led by Dr. Catherine Whitaker at the University of Massachusetts Amherst, analyzed Webb observations of a galaxy cluster called El Gordo. Using the gravitational lensing effect, they identified a background galaxy with a confirmed redshift of Z equals 16.7. That corresponds to a time just 250 million years after the Big Bang. The galaxy showed clear evidence of a rotating disk structure. Disk galaxies require angular momentum. They require time for gas and stars to settle into a stable rotating plane. The simulations that model galaxy formation universally show that disks do not form this early. They should not exist yet. But Webb's data clearly shows rotation. It clearly shows a structured disk. And the team spent months trying to find an error in their analysis before concluding the observation was real. Dr. Whitaker was careful in her public comments. She emphasized that this does not mean the Big Bang theory is wrong or that cosmology is broken. What it means is that the models describing how quickly structure forms in the early universe are missing something significant. Either dark matter behaves differently than we thought in the first few hundred million years, or the efficiency of star formation was far higher than current physics allows, or there's another process we have not accounted for that accelerates galaxy assembly. Now, let me be very clear about what this does and does not mean. This is not evidence against the Big Bang. The Big Bang is supported by multiple independent lines of evidence, including the cosmic microwave background, the abundance of light elements, and the large-scale structure of the universe. None of that has changed. What has changed is our understanding of the detailed timeline of how galaxies formed after the Big Bang. Think of it this way. We know the universe began roughly 13.8 billion years ago. We know it expanded and cooled. We know the first stars formed somewhere between 100 and 200 million years after the Big Bang. What we thought we knew was how long it took for those stars to gather into organized galaxies. We thought it was a slow, gradual process requiring 500 million to a billion years. Webb is showing us galaxies that look organized and mature appearing in less than 300 million years. That timeline does not fit. There are a few possible explanations currently being debated in the scientific literature. The first is that star formation in the very early universe was far more efficient than models predict. In the current universe, when gas collapses to form stars, only about 1 to 2% of the available gas actually turns into stars. The rest gets blown away by stellar winds and supernova explosions. If star formation efficiency in the early universe was 10 or even 20%, that would allow galaxies to build mass much faster. The second possibility is that our measurements of distance are wrong. Redshift tells us how much the universe has expanded since the light was emitted, but converting that into an actual distance and age requires assumptions about the expansion rate of the universe. If those assumptions are slightly off, the galaxies Webb is seeing might be younger than we think, which would give them more time to form. But this explanation has problems, because it would require the error to be systematic across dozens of independent measurements. That seems unlikely. The third possibility is the one that has physicists most interested and most concerned. Dark matter, which makes up about 85% of the matter in the universe, might behave differently in the extreme conditions of the early universe than it does today. Dark matter does not emit light, but it does exert gravity, and that gravity is what pulls normal matter together to form galaxies. If dark matter clumped together faster in the early universe, or if it interacted with normal matter in ways we have not accounted for, it could accelerate galaxy formation significantly. Testing this idea requires simulating the early universe with different dark matter properties, and seeing if the results match what Webb observes. Several teams are doing exactly that right now. Early results published in March 2025 suggest that a model called warm dark matter, as opposed to the standard cold dark matter model, might produce faster galaxy assembly. But warm dark matter introduces other problems, including predictions that do not match observations of the nearby universe. The model that fits the early universe breaks the late universe. That is not a solution. That is a new problem. There's also a fourth possibility that almost no one wants to say out loud, but that hangs over every conversation about this topic. It is possible that our understanding of gravity itself at cosmic scales is incomplete. General relativity has passed every test we have thrown at it for more than a century. But general relativity has never been tested in the conditions present 250 million years after the Big Bang. If gravity behaves even slightly differently under those extreme conditions, the timeline for structure formation could change dramatically. This is the most radical explanation, and the one with the least evidence. But it is on the table. What makes this moment in cosmology so significant is not that we found something unexpected. Science is full of surprises. What makes this significant is that we found something that conflicts with a model we thought was well understood. The standard model of cosmology, called lambda CDM, has been the dominant framework for understanding the universe for more than 20 years. It explains the cosmic microwave background. It explains the distribution of galaxies. It explains the accelerating expansion of the universe. It has been tested and confirmed by observation after observation. But lambda CDM makes specific predictions about how fast structure should form in the early universe. And Webb is showing us that those predictions are wrong, not slightly off, dramatically wrong. Galaxies are appearing hundreds of millions of years earlier than they should. They are more massive than they should be. They are more organized than they should be. Something is missing from the model. The response from the cosmology community has been methodical and serious. No one is panicking. No one is throwing out decades of work. What researchers are doing is what scientists do when observations do not match theory. They are checking the observations. They are refining the measurements. They are building new simulations. They are testing alternative explanations. And they are being very careful to separate what we know for certain from what we think we know. As of early 2026, the observations have held up. Multiple independent teams using different analysis methods have confirmed the existence of massive structured galaxies at redshifts above z equals 10. The data is real. What it means is still being worked out. Webb is continuing to observe. Every month brings new data from deeper surveys and longer exposures. The telescope is currently involved in a program called the JWST Advanced Deep Extragalactic Survey, or JDES, which is specifically designed to find and characterize the earliest galaxies. Results from the full survey are expected in late 2026 and early 2027. Those results will either confirm the pattern Webb has already found, or reveal that the early observations were somehow biased or incomplete. Here's what you need to understand. This is not a story about the universe being broken or science being wrong. This is a story about the process of science working exactly as it should. We built a tool capable of seeing farther and more clearly than ever before. That tool showed us something we did not expect. And now the scientific community is doing the hard work of figuring out what that means. The galaxies Webb has found at the edge of the observable universe are real. They exist. The light from them has traveled more than 13 billion years to reach us. What we are seeing is not an illusion or an error. It is a direct observation of the universe as it was in its infancy. And what that observation is telling us is that the infant universe was more complex, more active, and more capable of building structure than we gave it credit for. If you are finding this valuable, subscribe to Space Horizon right now, because this story is not over. Webb is still observing. New data is coming in every week. And as our understanding of the early universe shifts, we will be here covering it with the depth and accuracy it deserves. Drop a comment and tell me what you think is the most likely explanation. Is star formation in the early universe just more efficient than models predict? Is dark matter behaving differently than we thought? Or is there something deeper going on with our cosmological models? I read every comment, and the discussions that happen here are some of the best on the platform. Share this video with someone who still thinks the universe makes sense, because it turns out even the scientists studying it full-time are being forced to rethink assumptions they have held for decades. The edge of the universe is not where we thought it was, and what exists out there is not what we expected to find. Thanks for watching Space Horizon. We will see you in the next one.